Assalamu alaikum. My name is Shadi Mansi, and this lecture will be dedicated to explain the principle of operation of the transformer, and then I will go and move to your lab to explain what is happening in this experiment, single phase transformer. So as a start, we need to understand the principle of operation, and this is why I put this like general image. And I hope that this general image will be stuck in your mind, because when we are talking about transformer, please, your mind must bring this picture in front. Now, as you can see, the transformer basically it has the following items. The first item and the main one is the core. Can you see? This square shape is called the core, القلب. And then we have two coils. This coil number one and this is coil number two, each coil in a different side of the transformer. Now, this coil is called the primary because later on it will be connected to the power supply. And this coil is called the secondary because later on it will be connected to a load. Now, we have to put in our mind one more thing, that it doesn't supposed to mean that this one is going to work all the time as the primary and this one will be work as a secondary. It depends on the function of the transformer. So what is the main function of a transformer? The main function of the transformer is to step up or step down the voltage. So in this transformer, for example, as you can see here, the number of turns here is larger than the number of turns on the other side, which is the secondary. It means the voltage which will be at the secondary will be less than the voltage which will be at the primary. So this one is called a step down transformer. In other words, if we supply the primary with 100 volt, then we will generate here 100 volt, right? We will have here in the primary winding, we will have 100 volt. This 100 volt with the current which will move through the coil will generate a magnetic field. By the way, the power supply, it has to be AC. And then we will generate a AC current which will move through the winding, and this AC current will be the motive force to produce the magnetic field. Most of the magnetic field which will be generated by the primary current will be moving through the core, because it has less resistance to the magnetic field. So most of the generated magnetic field of the primary current will move through the core, and it will go through the secondary winding. Since it is AC magnetic field, and we have a conductor, then it's going to generate voltage at the secondary. The generated voltage at the secondary depends on the number of turns at the secondary winding. So let's assume in this case that the number of turns at the secondary is half the number of turns at the primary. So if we have 100 volt comes from a power supply and we have here 100 volt at the primary winding, then we will get 50 volt at the secondary. So this transformer is called a step-down transformer. Now, let's imagine that we have another story. We have 100 volt. Now, it is not a secondary anymore, if I can remove it. Let me see if I can remove it. No, I cannot. Anyway, now let's assume, just remove the secondary and the primary. Let's assume that this is the primary, and I connect the primary with 100 volt. The primary now is connected with 100 volt. Now, the secondary, because now in this case, this winding, this side of the transformer will be the secondary, then it will generate a voltage, and this voltage will be double the voltage comes from the primary. So if we have 100 volt here, we will get the double, because as we stated, the number of turns here will be more and double. So the voltage which we will get at this secondary will be 200 volt. So in other words, what I want to say, that the transformer can work either step up or step down based on the function you want to use in this transformer. Clear? So basically this is the transformer, and this is the first image I want you to have in your mind. Now I will go further and I will explain the principle of operation. Again, we said that we have the primary winding as we have it here. It will be connected to an AC power supply, and we have the core, the iron core, which has very small resistance to the magnetic field. Now, the main function of the iron or the core of the transformer to have the magnetic field which is generated by the primary winding and to have it move through this core. And later on, we will see that in the other side of the transformer, we will have the secondary winding. Now, one important point needs to be stated is that the primary must be connected to an AC power supply. It must be an AC power supply. Why is that? Because we need to generate an AC magnetic field inside the core. To explain it more, as you can see here, this is the power supply, AC power supply. So we have an AC current move through the primary winding, primary again because it's connected to the power supply. This alternating current will produce alternating magnetic field inside the core, okay? Now, since we have alternating current inside the core, alternating magnetic field inside the core, so we will generate voltage at the secondary. The value of the voltage, induced voltage at the secondary, depends mainly on the number of turns which we have it at the secondary. If the number of turns again of the secondary is greater than the number of turns of the primary, then this transformer works as a step-up transformer. If the number of turns at the secondary is less than the number of turns of the primary, then it will generate voltage less than, which comes from the primary, so it is a step-down transformer. This is very important. And the voltage which will be generated at the secondary, of course, is going to be an AC. And the good thing is that the frequency which we will get at the secondary will be exactly the same of the frequency comes from the power supply. So basically, we can use it at home. If we have, for example, a load which needs 120 volt, and the voltage which we have at home is only 220 volt. So I can bring a step down transformer. Again, step down transformer, because the voltage here is 120. The needed voltage 120, and the voltage I have 220. So I can bring a step down transformer which is going to step down the voltage at the secondary, or vice versa. If I have a load which needs 220, let's assume another case, another scenario. I have another load which needs 220 volt, but unfortunately the only voltage I have in my home is 120. So I can bring another transformer which is called step up transformer. So it can step up the voltage which is 120 up to 220 at the secondary, so I can connect the load to the secondary. Now, please note that the primary winding is the side of the transformer which will be connected to the power supply. The secondary winding is the part which will be connected to the load. The only changing here is the voltage level, and definitely the current will be changes according to the voltage induced by the secondary. So the only two variables which will be changed are the voltage and the current, and the frequency will be what? Where the frequency will be fixed. Now, instead, like drawing the transformer all the time like this, especially if we have a lab and you want to explain something, we have another schematic diagram to explain and to represent the transformer. They are the same, as you can see. Here, this transformer is exactly the same as this transformer. We have an AC power supply. We have a switch. It's going to be, for example, to switch on the power or switch it off. So it's part of the power supply. And then here we have a winding here. And then these two lines, these two parallel lines represents the core because we are transferring the magnetic field. And then we have what? We have the secondary. Now, again, the power supply must be AC. We cannot connect DC power supply to transformer and we expect that the transformer is going to generate the voltage, because, again, I forget to emphasize on this important point, because we must have an oscillating flux magnetic field that is changing with time, because this is the main principle in order to generate voltage at the secondary. So if we go back here to this schematic diagram, which represents the transformer operation, we can see all the time that we have AC power supply connected to the primary. This one, as we said, the two parallel line represents the magnetic field, the core of the transformer, and then we have the secondary. Now, as we said, the secondary at the end, it has to be connected to a load, maybe a refrigerator, heater, lamp, or whatever. So from this time on, if we are talking about transformer, expect to see this picture from this time on. Now, let's have this question and try to understand the principle of operation of a transformer with numerical value. Let's assume we have here like a 28-volt AC. This is the power supply connected to this transformer. So basically this is the primary, right? And this will be the secondary, and the secondary is connected to a load which has 350 ohms pure resistive load, and the secondary, the primary is already connected to a power supply. There is no load at all here. It is only the power supply connected to the primary. The other side of the transformer where we have the secondary is connected to the load. Now, you can see here the number of turns. Number of turns is very important in the transformer to understand the operation of the transformer. You can see at the primary we have like 2,390 turns, where the secondary it has 710. So this transformer, we can conclude that this transformer works as a step-down transformer because the number of turns at the secondary is less than the number of turns at the primary. So this will introduce us to conclude that we have a ratio of the generated voltage in the secondary, and this ratio, it is the relationship between the voltage comes from the primary, the ratio is the relationship between the voltage which comes from the primary to the voltage which will be generated at the secondary. And the ratio is usually called K, some other they call it A, some other they call it N, and so on. It depends on the book. So it is like a notation. So I put it like a K, a constant. The turns ratio, which is the number of turns at the primary, P stands for primary, S stands for what? Stands for secondary. So number of turns at the primary over the number of turns of the secondary, we call it K. So the number of turns, if I want to calculate it, we can say that the number of turns here equals 2,390 over 710, and this will be equal to 3.3662. So this is the turns ratio. And as you can see, if the turns ratio, later on we will even talk about it, if it is more than one, then we conclude that this transformer is a step-down transformer. If the turns ratio less than one, between 0 and 1, it's a fraction number, then it means that this is a step-up transformer. So in this case, the turns ratio is a 3.366, so we conclude that this transformer works as a step-down transformer. Now, the question is, calculate the load current and the load voltage in this transformer circuit. So in other words, this is the load. We need to figure out what is the current moves through this circuit, which is the secondary only, and the voltage which will be applied to the load, which is the V secondary. So from this, like the turns ratio, we can conclude also the voltage, because the turns ratio is equal to the voltage ratio. Again, the voltage ratio is the ratio between the voltage in the primary to the voltage in the secondary. So as you can see here, that the 3.3662 equals what? It is equal the voltage of the primary over the voltage of the secondary. So the voltage of the primary equals 227, right? So in order to find the V secondary, we can divide V primary over K. We can find V secondary because K, if I want to put it like this, just a minute. Okay. I have just, my computer is a little bit slow, so you just cope with me. So I'm going to put it here. So the turns ratio equals the voltage ratio equal V primary over V secondary, right? But now, if we want to find V secondary, we can conclude again that V secondary, Control X, I'll put it here. This is V secondary. equals, I will take K and I will put it here, and I will remove this part. So V secondary is equal V primary over K, right? K equal V primary over V secondary. So V secondary is equal V primary over K. So in this case, I can figure out what is the voltage which will be generated at the secondary. So it will be equal to V secondary equals, so V secondary equals V primary, which is 28 volt, over the turns ratio, which is 3.36 plus, so this will be copy over here, and this is equal to 8.318 volt. So the voltage of the secondary will be 8.318 volt. Okay, so what will be the current at the secondary? So I can conclude also that the current at the secondary equals what? It is equal the voltage times the resistor. So the voltage equals to 8.3, copy, paste, times what? Times 350. And this is equal to 2.8 ampere. Clear? So this is the current and the voltage at the secondary. Now, I will ask you in your report, the final report, to answer these two assignment questions. The first one, as you can see here, we have 110 volt AC at the primary, connected to the primary, which we have 1,400 turns, and the secondary, as you can see here, we have number of turns is much higher than the primary, which is equal to 3,610 turns, right? And it is connected to a load which is 3.9 kilo ohm. So we need to figure out what is the I source, which is the I primary, and I load, which is I secondary. Now, I will go back here and I will add one important note, that the turns ratio equals to, control copy, sorry, control Z, control copy, okay, control paste. It is equal, actually, X, paste, X, copy me please, just a minute. Okay, sorry. Control X, control. Actually, here I'm going to put I primary, I secondary, sorry, over I primary. So here I'm going to remove it, and here I'm going to put I, and I will remove the S. So as you can see here, the turns ratio, which is equal, the voltage ratio is equal. Here we see V primary over V secondary, but for the current it is vice versa. So if I want to figure out, this is the I secondary, if I want to find what is the current at the primary for the same question, because I figured out what is the voltage here and what is the current at the secondary, I need to find the current at the source, which is the primary. So I can find it like this. You know, I primary will be equal, or the source current will be equal what? Will be equal, as you can see, I need to find I source, right? Which is, sorry, I secondary, this one. I need to find I primary. So I primary will be equal I secondary over K. So it is equal I secondary, which is 2. You know, I have something wrong here. Voltage over current. Sorry, voltage over. This one must be over. I have something wrong here. Equals. Okay, so this is the current. Oh, well, it makes sense. It makes sense now. This is the current at the secondary, because this one, the voltage over R equals I. This is the source, sorry, the secondary current. So if I want to find the primary current, it will be as follow. I primary, again, it is equal I secondary over I primary. So it will be the current over K, and K equals to 3.3, right? So I will take it, copy, put it here, and this is the value of the current. So as you can see, the value of the current, it is equal like 7 milliampere. Okay, so the same thing you have to apply it here. For example, in this question, you need to find, first of all, you need to find the voltage at the primary, at the secondary. Okay, then you can find the current at the secondary. Then you can find the current at the primary. So the first thing ever you have to find, if you have any transformer question, is to start with the turns ratio or the voltage ratio. You have to figure it out. You have to find it. What is K for this transformer? Then the turns ratio or the voltage ratio. Then you can find out all the other missing items. Same thing, it applies here for this question. We have, as you can see, this is the primary, not this. This part, this side is the primary. It is connected to 3.7 volt AC. It's very small amount of voltage. And we have number of turns is 400. And at the secondary, we have 13,000 number of turns at the secondary, and it's connected to 1.5 kilo ohm. So all what you need to find in what is V primary, I think it is here. What is V secondary? What is the voltage as the secondary? What is the current? You need to figure out the current at the secondary, then you can figure out the current at the primary. Okay, so I prefer to, or I will ask you to solve this assignment. I'm expecting to find assignment 1 and assignment 2 to be solved in your final report. Okay, now we will go to our experiment. But before we go to the experiment, I just want to emphasize on one thing. You know, sometimes we have in one side more than one coil. It happens. It happens. So if I go back to this lecture, we could have like one coil and we have another coil. In the secondary, we could have one coil and another coil and another coil and another coil and so on. So you have to choose which coil you want to use, or you can connect these coils together so you will have a cumulative voltage at the secondary, for example. Or the primary, we have, you know, like coil for 120, another coil for 220, and so on. So if we go to this type of transformer, where we have more than one coil, for example, this transformer, and it suggests that this is the primary can work for 240 or 480 volt. How is that? By each coil, for example, here, it can handle 240. So if I connect H1 and H2 to the power supply, so the power supply must be 240. But if I have more power supply and I need to have more voltage, so I can connect these transformers together, so 220, 240 and 240, and H1 and H4 will be connected to the power supply, so I can connect the primary to the voltage, which is equal to 480 volt. The transformer, we have it in our lab, looks like this. We have terminal 1, terminal 2, okay? We have terminal 3 and terminal 4, and we have terminal 5, as you can see here, and terminal 6. For terminal 5 and terminal 6, we have two coils, as you can see it here, right? And in the middle, we have terminal number 9. So I can take only terminal 5 and terminal 6. Or you could have terminal 5 up to terminal 6, okay, where terminal 9 will be not used. So you are taking the two coils together. In some cases, for example, as we can have here in terminal between terminal 3 to terminal 4, we have 3 to 7, or you can take 7 to 8, or 8 to 4, or 4 to 7. You can choose which coils you will use in your connection. You can see here that terminal 1 to 2, the rating voltage is 120. Just a minute. So this one is 120 volt. Let me maximize it a little bit. Okay. So between terminal 1 and terminal 2, this coil can handle 120 volt. Terminal 3 to 7 can handle 104. Terminal 7 to 8 can handle 76 volt. Terminal 8 to terminal 4 can handle, I think, 28 volt. So if I put all of these coils together and I measure the voltage between terminal 3 to terminal 4, I will get the voltage, the summation of the whole voltages, which will be 104 plus 67 plus 28, which is equal to 208 volt. Now, terminal 5 to terminal 9 is 60 volt. And terminal 9 to terminal 6 is 60 volt. If I take it from 5 to 6, then 60 plus 60 is 120 volt. Okay? So let's go to our experiment and let's see what we have. As you can see, this is basically your experiment, which is the single phase transformer. In the single phase transformer, we have the procedures and what we have to do. Now, it will ask you, connect the transformer, this transformer, connect it to the power supply, because all the time I'm going to refer to this terminal of the transformer. So we will connect terminal 1 and 2 to the power supply with the rating voltage 120 volt. Then you are asked to fill out the blanks here. Now, terminal 1 to 2, we will get 120. Terminal 3 to 4, where is terminal 3 to 4? 3 to 4, we will get 208, the summation, because if you put the voltmeter between 3 and 4, you will get the voltage, the summation of all voltage, which will be generated at these windings. By the way, 1 and 2 is connected to the power supply. So terminal 1 and 2, this coil is the primary, and the other coils, all the other coils will be what? Will be the secondary. Now, what about terminal 3 to 7? 3 to 7, here it is. This is 3 to 7. I'm expecting 104. 104, exactly. Terminal 7 to 8. So this is 7 to 8. 7 to 8, the voltage, the rated voltage is 76. Since you applied rating voltage, so I will get 76 volt. Okay, and so on. It goes through all of these connections. 5 to 9, it is 60. 9 to 6 is 60. But if it is between 5 and 6, it will be 108 volt. Okay, now these are the rating current, the maximum current that this transformer can handle. It is also indicated here. As you can see, they are indicated in the transformer. Sorry. Now, using the lowest range of your ohm meter, we can measure now the internal resistance. Of course, the internal resistance basically depends on the coil. If we have, as we have number of turns will be increased, then we are expecting more voltage at the secondary, right? So far, so good. Now, let's go to the schematic diagram for our transformer. As you can see, this is what we have done. Terminal 1 and 2, terminal 1 and 2 will be connected to the power supply, the variable power supply AC from 0 to 120. So it was terminal 4 and the neutral of the AC power supply, and it's connected to terminal 1 and 2. As you can see now, we have like two secondaries. We have so many windings in this transformer. Terminal 3 to terminal 4, we have this big transformer where we have other exit points, which is going to be terminal 7 and terminal 8, which are represented here. This is terminal 3 to terminal 4. It looks like one big giant transformer, but we have exit points in the middle. And then, we have another also secondary big transformer or big winding from terminal 5 to terminal 6. And in the center, exactly at the center, in the middle, we have an exit point, which is number 9. If we go back here, 5 to 6, it is like one transformer and split it in the middle with number 9. So this is why we have 60, 60, okay? But if you take the whole winding from 5 to 6, we will get 120 volt, okay? So basically, this is how the transformer is looking, how it looks like. Now, to solve any problem with this type of transformer, we need to identify where is the primary. I will go back here. Where is the primary? Where is the secondary? Because you cannot use all the windings all together. Now let's assume, and most of the cases, terminal 1 and 2 will be the primary. And let's assume terminal 5 and 6 will be the secondary, okay? Now, to solve any questions related to the voltage, you need to figure out what is the voltage ratio. Do you remember the voltage ratio? So we will go here and we will say that the voltage here between 1 and 2, this is the V primary equal 120, V secondary equals 60. So the turns ratio will be 120 over 60, which is equal to 2. So since it is greater than 1, so it is a step-down transformer. Obviously, it's a step-down transformer. Now, if you apply 120 volt, because this is the rating voltage, you will get 60 volt, right? But what if we apply 100 volt? This is a good question because you will find it later on in the review questions. What if I apply 100 volt at the primary, which is 1 and 2? I did not apply 120, which is supposed to be because this is the rating voltage, but I applied another voltage, which is 100 volt. So what will be the voltage I'm expecting at the secondary, because I'm choosing 5 and 9 as the secondary. These are the terminal. To answer this question, we have to go first of all to the voltage ratio. The voltage ratio is 120 over 60, right? So it is equal to, now we didn't apply 120, we applied 100 voltage. So 100 voltage divided by K, which is the voltage ratio. So we will get here 50 volt. So if you applied 100 volt, you will get here 50 volt. If you applied 50 volt at this primary, assuming that this is primary, so you will get at the secondary 5 and 9, you will get half of it 50, so the half of it is going to be 25, and so on. If we assume that this is the primary, and this assume that 7 and 8 is the secondary, so if we apply 120, we will get at the secondary 7 and 8, 76 volt. But what if we apply 100 volt? If we apply 100 volt, so you need to figure out what is the voltage ratio. So again, in any transformer question, you have to go first to the voltage ratio, and from the voltage ratio, you can solve all the questions because you know the voltage at the primary, you have the voltage ratio, you can figure out the voltage at the secondary, and from the voltage at the secondary, you can figure out the current at the secondary. From the current at the secondary, you can find the current at the primary. And voila, you solved all things related to like transformer primary and secondary issue. Okay, clear, Shabab? So these are the most important part I need to cover in this video. Now let's move on. Do you measure voltage corresponding well? I will not go through all of these questions, and as you can see here, calculate the current ratio. We will calculate the voltage. Here we have the winding ratio. If the winding is 1 and 2 and 5 and 6 each have like 500 turns, so we have to find the turns ratio, which is equal to the voltage ratio, and so on. For example, in this question, we have terminal 1 and 2 is the primary, terminal 3 and 4 is the secondary, and we applied here, let's assume 120 volts, so we will get in the terminal 3 and 4, this is terminal 3 and 4, we will get 208 volt. Obviously, we will get this voltage at the secondary. This is 1 and 2, 5 and 6. Now, if we apply 1 and 2 as a primary because connected to the power supply, and the secondary is 5 and 6, this is secondary. So 1 and 2 is the primary, 5 and 6 is the secondary. So we will get the voltages based on the turns ratio and how much voltage you applied at the primary, so we can figure out the voltage at the secondary. Okay, Shabab. So basically, this is all what I need to cover in this transformer issue. And now to conclude, I need to explain like two concepts, okay, and then we will close this chapter. Now, here again, to wrap up, we said that we have primary, we have secondary. We need to figure out K, which is the turns ratio between primary and secondary, and it is exactly equal the voltage ratio, which is V primary over V secondary, right? For any problem, we need to figure out the voltage ratio. We know the voltage at the primary, so we can conclude and calculate the voltage at the secondary. And from the calculation, we can figure out the current, because if you have the voltage here, you have the load here, divide the voltage over the load, you can get the current. If you have the current at the secondary, you can calculate the current at the primary as we did in the old example, right? So this is the wrapping up for any transformer. Now I need to add two major points. The first point is that the transformer assumes that it is ideal. It means that we don't have losses. But actually, when it comes to reality, we have losses. And the losses comes from that we have a copper winding. So when the current moves at the primary, some of the energy which comes from the power supply will be lost inside the copper because we have a current, we have resistors, so we have drop voltage here, small drop voltage, and this is we call it copper losses. And we have another losses which is going to be the iron core. This iron core will consume some of the magnetic field because we said the magnetic field will move through the core, and we choose the core which has less resistance to the magnetic field. So most of the magnetic field will move through the core. However, this core still has a resistance to a magnetic field. So part of this energy which comes from the main power supply and it was converted into magnetic field will be lost inside the transformer. And this is by the way, why we have the transformer after, like running for 1 hour or 30 minutes, 15 minutes, it is heated up because we have inside the core, we have a resistance for the magnetic field, and this is why it will be heated up. And we have another couple losses in the winding, but these losses are very small. The losses are very small. It's not that big, like 20, 30% or 70%. No, it is very small, like 10% in average. And this is why, in theory, we say that we assume we have an ideal transformer. Ideal transformer means that we don't have losses, but in reality, we have losses. But in theory, when we have like questions in theory, we assume that we don't have losses at all. And in this case, the power here, the input power will be equal to the output power. Okay, the input power must be equal to the output power at the secondary. By the way, this machine, we call it a machine because it converts the electrical power to another form or another electrical power with different level of voltage and current, but it is a machine. So we have input power, we have output power. And don't forget, we are talking about AC machine, okay? The input power in ideal transformer equals to the output power, okay? But if you want to calculate the efficiency, calculate the power at the secondary, divided the power over the power, not the voltage, the power at the primary, we can get the efficiency of the transformer. Don't forget that we are working with AC, so if this is a single phase, so it is equal V primary times I primary. This is the power at the primary. The power at the secondary equal V secondary times I secondary. So this is the power at the secondary. And the unit of this power will be in volt ampere. So if I want to write it here, so I'm going to write the power, just a minute. So the power at the primary equals V primary times I primary, right? And this P, okay? And this must be equal to the power at the secondary. The power at the secondary. Now, the power at the secondary equals V secondary times I secondary, okay? And both of these must be equal. And this is why it comes the fact that if we have a step-up transformer, or in this case, this is a step-down transformer. If we have a step-down transformer, so the voltage at the secondary will be less than the voltage of the primary, right? But at the same time, the current at the secondary will be greater than the current at the primary. And this happens because we want to maintain the power issue. It has to be the same, the power, it must be the same. So if I reduce the voltage, by default, the current will be increased, okay? It will be greater than the current of the primary to maintain the equation that the power of the primary equal the power at the secondary. Okay, Shabab? So I think I explained all what I need to do with the transformer. I wish you all the best and thank you for listening.